Good evening. Hear me, right? Ravi, he's a physics teacher and he's currently secretary of the Physics Society, and he's very passionate about physics and education. And his aim is to, make education more relevant and more, provide more value to the meaning of education. That's his mission and passion. And he has taught in Padma Sheshadri here and also American International School as a teacher. And he's full-time into teaching physics. And of course, I've told you about the fan following he has and the kind of passion he brings into the field. And sir, over to you to the session. Thank you. Thank you, sir.
Thank you, Gopal. So we'll get out of business straight away. The topic is pendulum, but because I'm a physics teacher, I don't want to talk anything other than physics. But I know there's a general audience as well, so I'm going to make it. I'm going to base it on pendulum, but it's about thinking. And I chose pendulum because I'm sure most of you in school days would have done some pendulum experiment. You would have seen a pendulum or worked with the pendulum. You've done something. So I thought that would be a topic which I could connect to and probably take you, go back to your school days and make you feel younger than what you are now. Younger than.
You are young together.
I included you. Oh. Okay, so how do you start it? Oh, that's okay. Well, so that's a topic here, learning to think. I put quotes on simple because I don't like it. I mean, sometimes I talk about pendulum for 1 full hour, the math of it and the physics, detailed physics. But here I'm going to make it more general. And as a teacher, I'm somebody who hates PowerPoint. I hate PowerPoint. I remember when I was in American school, when I give some projects, students go for PowerPoint. So a project is basically an application of PowerPoint, chart papers, thermocol. So I said no to PowerPoint. But today, it's fate, I would say. I'm going to take, you make use of the PowerPoint. So PowerPoint is not going to replace me. So I hope I can put PowerPoint to good use. So that's why the advertisement, say no to PowerPoint. Okay. Let's get down to business. Now, what's in store for the day? And I would like some of you to tell me, what do you expect from today's session? Some of you have been my students, so I would want you to refrain from taking part much. But others, would you mind sharing what do you expect from today's session? You have come here with some hope. Can I have it from you? Is there a microphone?
Hello, my name is Ruven, and we are students from Germany. We are exchange students, and we are taking part in the knowledge management course at IIT. And we've been invited by our professor. It was very nice. So I expect from today's session maybe to learn about a little bit more about the system of thinking and maybe the system of learning. And maybe there could be some insights for us to maybe have some improvements in our own thinking in the future.
Wonderful. Thank you for that. See some parents also. I like to have some parents share some thoughts. Yeah?
Hello, this is Mohan. I think I have come with my daughter. She was a student of Mr. Ravi. So what I expect is from your topic, what I could gather is maybe you will teach us how to think out of the box. We always talk of thinking out of the box. Maybe that could be one learning from this session.
Maybe. Let's try. So I think I can start. I think I'll go ahead. So let's begin with some, before we get down to serious stuff, a bit of wiki trivia. So pendulum, mostly Galileo is associated with that because it seems that he studied pendulum a lot and he explored how a pendulum's oscillation, he studied the pendulum's oscillation and he studied how the time period of the pendulum, the time it takes to swing. I did get a very simple pendulum. This is what I could gather from my house. I got a piece of thread and a stapler. So simple pendulum, let's keep it simple. So it swings like this. So he studied its motion. Studied its motion is very crude. He was an experimental physicist. So I would say one of the first few people to put science on a firm experimental basis. So this is called length of the pendulum. I'll tell you more details as we move on. Length. And you can have some mass for this bob, so to say, and then you can allow it to swing. So it takes some time to go from here to there and back here. So this is the measurable quantity, the time it takes to make a swing. Now he studied how the time it takes to swing depends on the length and the mass and some other parameters. So I didn't take the trouble of finding out what he exactly did, but maybe he could explore that. But I didn't bother to find out. Then pendulum clocks. This is Huygens of wave theory fame. It seems that he was the first person to make the pendulum clock. Now it's outdated, but it's a very curious thing. In fact, I've been trying to get a pendulum clock at my home, and because it's very intriguing, the mechanism is very complicated, and it's an oscillator, isn't it? It's a maintained oscillator. Its oscillations are maintained in it somehow. It's very interesting because this normal pendulum stops after some time. A pendulum clock, at least a grandfather's pendulum clock, runs for a few days at least. So there is a mechanism which keeps it going for a long duration. So how is it achieved? That's an interesting topic to discuss. Not which I have mastered. I have not understood that, so I didn't bother. I didn't find out. Maybe I should try to find out. And those of you doing electronics engineering would also relate it to the electronic oscillator. This is a mechanical oscillator, and it's analogous to the electronic oscillator you will read in electronics engineering. So that's about Huygens. And pendulum clocks. I read an article which said pendulum clocks were in fashion till about 1927. Of course, people still do use it. After that, we had other types of clocks. So mostly time measurement was using pendulum clocks for a long time, at least 200 years. And then this is something called Foucault's pendulum. You know, the Earth rotates about its own axis. And this guy called Foucault, he designed an arrangement by which, using a pendulum, you can understand that Earth's rotating. I mean, I don't know the mechanism of it. I mean, I know it's just a pendulum, but I don't know the physics behind how a simple pendulum could help you to understand that Earth's rotating about its axis. And you do see this Foucault's pendulum in many science centers and even in universities. The Periyar Science Center did have one many years ago. I'm not too sure if it has one, but many science centers world over, universities world over do have it. I have a few pictures to share with you. I'm not too sure if that's so clear from wherever you are. Maybe I need to put off the light. It's a very long pendulum suspended, and there's a heavy ball. It's a very heavy ball that keeps swinging, and it's not powered. Since it's very heavy, the oscillations will not get damped that soon. The length is usually a few meters. So that's what would happen is, during the course of the day, as it swings, normally you think the pendulum swings in a single plane, right? This is called plane of oscillation. It swings in a plane, but wait for a long time during the day. Initially start like this. After some time, it will slowly change its plane this way and this way. Not this fast. It takes a day. So it changes its plane of oscillation. But I don't know the exact physics behind it, but I thought I'd share that with you. And I went to the University of Seattle once, University of Washington in Seattle, and it was exciting to see a Foucault's pendulum there. When the length was about a few meters, and this is a Foucault pendulum in University of Washington, Seattle. This is the top view of it. Can you see a huge ball there? And that will it will keep swinging, and its plane of oscillation will change, and that's not trivial. Okay, that's the most important slide. Anyways, I have a video to show there. You can see it swinging. I took a video, so you can see the pendulum swinging. But don't expect to notice its the change in the plane of oscillation. That's going to take a long time. And another one. How do I go to the next one? Oh yeah. It doesn't look that way. Oops. Oh, yeah. This is another video. Same place. can see the length. I think it's at least 7 or 8 meters. See that? Goes up there, I think easily 8 meters, easily 8 to 10 meters. It's a long pendulum. For those of you who are into physics, the idea is it's a long pendulum at a heavy mass, its moment of inertia is very large. Since the moment of inertia is very large and the air resistance is not sufficient to stop in a short span of time. So that's the idea of having a long pendulum and a heavy metallic a ball at the bottom. That's the concept. Oops. Okay. The pendulum man. So the human body itself is a complex of multiple pendulums. So in fact, I have a small toy for that. So I went to a shop in somewhere in the US and they had this. So it's multiple oscillators. And we are a bunch of pendulums. So our human body is just here. There's pendulum here, there's pendulum here. See? So Ravishankar is just many pendulums put together, you have a human being. So so human body is just multiple pendulums. But it's a very complex pendulum because number one, look at the number of degrees of freedom. It's very complicated. The technical term for that is called degrees of freedom because this can swing like this can swing like this can swing. So I am more complicated because see this, each finger will be an oscillator. See this 1, 2, 3, 4, then here, then here, then here. There's so many oscillators. Here there's an oscillator, here there's an oscillator, here there's an oscillator, here. I mean, many oscillators put together. So certainly that can't be counted as a piece of trivia. Okay, let's now get some more serious business. The topic is simple pendulum. So I want you to talk to each other and come up with a definition for simple pendulum. What would you define as a simple pendulum? I mean, I've been talking pendulum and simple pendulum. Just talk to each other 2 minutes. Talk to each other and find out. I want a definition. What is your understanding of a simple pendulum? Talk to each other. 2 minutes. Please talk. It's okay. Talk to each other. And I would want a response from you, by the way. I would want you to respond. The idea of asking for a definition is, I mean, in science you need to be precise. If you say, if you use a word, you got to define what you're talking about. Otherwise, how do I know what you think? Okay, can I hear from some of you? How you define a simple pendulum? Anybody who would like to define a simple pendulum? Virupakshan, come on, let me ask from you. You were a physics student once, come on.
Hey, by the way,
sit down.
We both were from the same batch. We did physics together and our professor was Ananthan. I'm not going to answer this question now.
Okay.
Okay.
He doesn't know.
I do not know. I do not know.
You believe me?
Gopal
Yes.
forgot to mention one thing. Whatever passion I used to talk about here is education, and we both come from the same professor, Professor Ananthan. We want to change the education system. So thanks for giving me the mic to give this information. Anybody else want to talk about it? Simple pendulum.
Oh. just tell something, it's okay. Come on.
Any object hanging from a string,
Eh,
oscillating,
Hold closer.
Any object
hang-
hanging from a string and then oscillating. Okay, fine, fair enough. So let's see. So let me provide you one more response, okay? Let's have one more response.
Any purposeful oscillator.
Sorry?
Purposeful oscillator.
Purposeful oscillator. Would you like to tell us like what is purposeful in the sense? Okay, fine. You want to say something? Manikandan was a more precise physics definition. Okay. Right, Manikandan.
I think any oscillation which follows the differential equation x double dot is minus omega square.
Why did we allow him here? Why did we allow him here? Why did we allow him here? Yes.
It's an object with attached to a string of fixed length from a fixed support allowed to oscillate.
Okay.
Object of negligible volume.
Negligible volume. Okay. I think that should be enough. That should be enough. Now, let me present the definition. Look at this definition. It says a point mass tied to a massless, inextensible string suspended from a rigid support. It's a point mass. Now look at the definition carefully. I'll read the definition. A point mass tied to a massless, inextensible string and suspended from a rigid support. Now I have a pendulum, right? That's a pendulum here. Now would you call this as a pendulum by my definition? Tell me, give me reasons why you wouldn't call this as a pendulum by my definition. One at a time, Mahesh. This is not a point object. A point object must have zero size. Anybody else? No string is inextensible. This looks like inextensible, but it will stretch a little bit. It will certainly stretch a little bit. So this is not okay. My hand is not rigid. I'm dancing along the pendulum, right? And anything else you like to say? I said a string is massless. No string is massless. Okay, let's say by the way, Manikanta, let me correct you. Manikanta gave the definition of simple pendulum. My question was pendulum. So this is just a pendulum. Now whether it's simple or not, it's a different. It depends on the motion. I'll come to that a bit later. So I wanted a definition of what is a pendulum. Now let's say you are in a class, 9th standard. This is an old topic. You've done it long back. You are in a class. The teacher comes to you and says, "Hey, this is a definition." And the teacher gives a definition. And we all are obedient students. We are brought up in a culture which is very obedient. And whatever the teacher says must be correct. Now, I want you to be rebels in a classroom. I mean, in a class, I want students to be rebels. You should read this book by Freeman Dyson. He says, the book is called The Scientist as a Rebel. If you look at great ideas in science, most of them have been rebels. Galileo. I mean, we talk so much about Galileo, but in his time, the church was against him completely. So he had a tough time. So great ideas come from rebels. So if you are in your class, or in my class, if I find a disobedient student, I see a Galileo in him. Right? I see a Galileo in him. Now, let's say the teacher gives such a definition. How would you respond to the teacher? The teacher says, hey, this is the definition of a pendulum. How do you respond to it? Anybody? Yeah? It's a useless, look at this, useless definition. Okay, my friend says, what nonsense is this? Why would I sit in this fellow's class? There's nothing like a rigid support. No point mass in this world. The object, any object has a size. Any string has mass. It has got length. It's going to stretch. So why would you go for this? So some of that, some students would, one of the basis of science, I believe, is skepticism. You start doubting, and most importantly, the teacher. In my class, I want to be always in the dock. When I teach, I want to be in the dock all the time. So my students have to question me and trash me down, because only then they are learning. So I expect students to say, what's the point in having this definition, because you're going to have it and not going to have it in reality. So much that you probably will say, oh, these physics people are good for nothing. They can't do real life stuff. You see that? I'm in an imaginary world doing things which have absolutely no relevance, probably because you don't get in reality. But then the idea is this: sometimes in a problem, you may have two options. Either you go for a simplified problem, or you will not be able to solve the problem at all. It may be that complicated. So as a beginner, you start like this. Practically, this is a fairly good approximation, because the string is not that heavy compared to this object. The string doesn't stretch that much. The support is okay, not that rigid, but still is okay. So you will try to get a system which is close to it. But then, as a beginner, when you want to do calculation, it is this system you can start doing your calculations. It's something like this. Some students keep asking me when I do this topic in class, why do you make so many assumptions? Why don't you go to the complicated stuff straight away? Well, it's like asking in kindergarten school, asking your teacher when the teacher introduced the English alphabet. It's like asking, why don't you teach me Shakespearean poetry on day one? Why do you teach me ABCD? And unless you know the alphabet, You're not going to form the words, you can't get the sentences, the paragraphs, and only then the story comes. It takes time. So though I start like this, we will at some point in the course go to the real pendulum. So it's not that we're going to stop with this, but as a beginner, we start with this. But what is important, the part of the teacher is to caution the student and tell him, hey, we're not going to stop here. I mean, that most of us don't do. Most teachers, we don't do that because we just give the definition and it's a 2-mark question. It's not worth more than 2 minutes. Okay. Now, have you heard of these? Simple pendulum, compound pendulum, conical pendulum, and torsional pendulum. Now, what I gave was a definition of pendulum. This is pendulum. Now, if it moves like this, like it swings, then you call it simple pendulum. Let's say you make it go like this, in a cone, then you call it conical pendulum. Sometimes you could actually give a small twist. I mean, it's difficult here, but it will swing like, it will twist and turn like this. People call it torsion. It's called torsional pendulum. So, simple or conical depends on the type of motion. So, my question was only the pendulum. What Manikandan said was the equation, and that equation will fit what I call as a simple pendulum. So, the mathematical definition for what is a simple pendulum. Compound pendulum is what you have in reality. This is a compound pendulum. And when I told you, I am made up of many compound oscillators. Ravishankar is made up of many compound oscillators. So, okay, I'm going to take you back in time. Now, I want you to spend some time talking to each other and consider these questions for discussion. Now, you might have done this experiment or some other experiment when you were a school student. Now, questions I want you to consider are, what did we do in a physics lab? We go to a physics lab, what do you do in it? Did you enjoy your time doing experiments? The teacher said, there's a lab today. Did you enjoy it? Did you said, yes, today I'm going to do physics lab. I am excited. Right? I'm enjoying, I'm going to have a fun time in the physics lab. Did you think like that? What did you not like regarding the laboratory experiments? Is there something which you did not like? And the observation notebook. And we are in a culture, we have 2 notebooks for every lab experiment. The observation notebook was a record notebook. And what was transferable in your laboratory experience? Transferable means, in some of you would have studied physics long back and you are not doing anything close to physics. Right? So when you look back, you are not doing anything close to physics. For me, I am a physics teacher, fine, I have to live with it. But you are not a physics student, you are doing chemical engineering, you are a doctor, or let's say you are a chartered accountant. Now you are nothing to do with physics. So what were you doing there then? How was the experience in the physics laboratory, and how is it relevant today for you? Now, can you look back and say, yes, my time in the lab was well spent? Yes or no? Talk to each other. Just talk to each other, and I would love to hear some responses from you. Okay, I think that's 2 minutes. Is there a mic doing rounds there? Yeah. I want some of my students, I would want you to refrain from answering now. Maybe we can do that later. Others whom I do not know, or some of the parents here, yeah, some of your friends, Gopal. Why don't you ask them, some of your friends? Or why don't you tell? Did you remember doing the experiment?
I was scared of physics lab, sir.
You are scared of physics lab.
And more scared to get signed the record notebook because she'll beat me in the knuckles actually.
The teacher beat you in the knuckles. Okay. So can you recall, what did you do in the physics lab? How was the experience? What did you do in the physics lab?
I mean, actually, whatever ma'am taught in the class, we were supposed to actually replicate exactly step by step in the thing.
That is follow instructions.
Follow instructions.
Wonderful.
And then make sure you get the 9.8 or whatever follow.
Wonderful, that's wonderful.
If you don't get that, then we'll get a...
Yeah, she's right. Science is about precision, right? And she wants 9.8, you'll get it. Yeah.
So the entire experience was about following instructions and completing it.
Wonderful. Yeah. Thank you, Gopal. Anybody else would like to add to that? I'm looking at what did you not like in the laboratory experience? Yeah.
Excuse me.
Yeah, please.
What did we do in the physics lab? That's a question. I have something to talk on that.
Please.
I was a science graduate,
Okay.
BSc physics. Subsequently, I did my engineering. That's okay. But in the physics lab, as he rightly said, we did not like. We come here and try to understand. We could not understand anything. And at the end of the class or the lab, what we try to do is we have to get the answer. So we try to do the reverse. We used to have the Clark's tables in those days.
That's right.
There the answers were available. So we try to keep the answer, do the reverse working, and try to get the observation on the readings. Because it never used to come.
Good.
It never used to come. And people were not available to educate us how it has to be done. Because it's just a formality we complete. I'm talking about in 1978.
Same thing still. Don't worry.
Right?
Probably they're preparing you for not engineering, but reverse engineering.
Anybody else?
Anybody else would like to share something? Okay, maybe that should be good enough. Well, as Gopal said, what's happening is the teacher gives you a set of instructions and you merely follow. Now, if the aim of the laboratory experiments is to follow instructions, you don't need to do a physics lab for it. In a physics lab, you could do a biology experiment. After all, you're going to follow instruction, or you could do cooking. Come on. It is probably more purposeful, as one of my friends pointed out there. What were you doing? You're just following instructions. I have no clue why you do that. And what is transferable in it? I think you are just producing that assembly line. You see that? A bunch of people who simply follow what you're being told to do. Now it's at the bottom of the philosophy of science. There is no exploration. There is no originality. You don't try anything on your own. In fact, you will probably be penalized for doing something on your own, Gopal, right? So did you enjoy your time in the experiment lab? No, see that? And I remember when I was a student, 5th standard, when they said 6th standard onwards, you'll have lab experiments. I thought, yeah, wow, they're going to do the lab experiments. 7th standard, I was wondering, oh, should you really go to the lab? Gone. In 1 year, they chopped it off. Because you're going to follow instructions, and more often, as Gopal rightly pointed out, you end up just pleasing the teacher, isn't it? What does the teacher want? Nice headings underlined, you write in color pencil, and you all do all this stuff, like packaging nonsense. End of the day, it's really, I'm sure people don't like me telling all this, some of them don't like it, but the point is, that's what is happening. Because there's no exploration, you're just following some instructions, and clearly there's no excitement which people say there is in science. And at the earliest opportunity, you want to pack up and go away from science. And you're still left over, you become a teacher like me. So, and then we have the observation and record notebook. You do the experiment, you take the readings in one notebook, and then you get it signed with the teacher. She has to say, yes, you're right. Because she is the authority. Sadly, what I don't like in the approach is, we attach a lot of value to authority in our system. In science, there is no authority. And if there is authority, you question. If somebody claims he is the authority, I think your job is to question the authority, not to listen to the authority. So you should be questioning authority rather than simply meekly submitting to the authority, which is in this case, the all-knowing teacher. And then the 2 notebooks, the observation, and you faithfully copy into the record note and get it signed. I remember I had a conversation with an American colleague of mine, and she asked me, Ravi, how do you do the physics? How do you do the labs in Indian system? I told her this is what we do. You know what she said? Ravi, that is sheer duplication of human labor. That's what she said. She said, Ravi, that the sheer duplication of human labor. Look at that. That's strong. A strong indictment, I would say, on what's the rot in the system. And almost every experiment is done like that. Almost every subject is like that. I can tell you, because I have done physics, chemistry and math, physics, chemistry and what other lab you do, computer science, it's the same thing, pretty much. Biology can't be any better. And finally the issue is, what is transferable? What is transferable? What is the gain? Did you pick up some skills? I mean, you need to pick up investigatory skills which can be transferable into any subject you branch off later on. Now that is sadly not happening. Next, so let's cut short here. How did you go to the laboratory? You follow the teacher. What is the role of the teacher? As Gopal said, the man with the stick who beats you on the knuckles if you don't follow orders. So basically you are a servant, right? I mean, it's a very slavish mindset that's instilled in you. And then what was the eureka moment, and was there one? Did you say, yes, I have done this today, I'm excited, right? And what are the learning takeaways? When you come out of the lab, do you come out excited? Yes, I learned this today, I'm going to come back tomorrow and day after. You don't want to, right? So that's a sad story. And Gopal said, what is the aim of the experiment? The teacher says, hey, let's find the acceleration due to gravity. Who cares? Do you bother? I mean, the focus unfortunately is on finding the gravity acceleration. So what? Why do you want to find that out? It's one student asked me years ago, he said, Mr. Ravi is known to everybody. Why should I find it again? Everybody in the world knows it. It's there in the book. If I want to find out, I can always refer a book and find out, why are you asking me to do something which is done already? Now, how do you answer this question in the classroom? This student wants a reason for doing the lab. Can we give a reason? No. So, who cares? And then, why do you teach this topic? I mean, as much as I'm talking about this topic, why would Ravishankar teach this topic? Do we have an answer? I remember when I was in American school again, I was doing math. I was teaching math and I was doing algebra. I was doing trigonometry, triangles and all that. I had a girl in the class. I was telling, it's an exciting topic. And I would be excited because at least I had to pretend because I need to get my salary. So I need to pretend at least that I'm excited. So I said, this is an exciting topic. You know what she said? Mr. Ravi, why would anybody get excited about triangles? Why are you teaching this topic? And then she continued, no, this is the student you want in the class. This is the student you want in the class. And she continued saying, she said, Mr. Ravi, my dad is an electrical engineer. I don't see him doing all this stuff. So even if I want to become an electrical engineer, you are doing things I don't need. So this student is demanding a reason why I am teaching this topic. So she wanted an answer. If I don't even answer and I move on, I am losing a student in the class. And if I lose one student, I can tell you she's going to tell this to other people, I'm going to lose the whole class. Now this is the moment which I can grab or I lose. My first response was this. I told her, well, I do this because it's there in the syllabus. Very exciting answer, isn't it? The student will get inspired to learn the topic. I continued. Second reason, I need to get my salary. The second reason, which I'm sure very convincing for the student to be in my class and learn trigonometry. Then I said, third one I said, well, I'm teaching this topic because you signed up for this course. You took math course. Did I ask you to join this course? You had the freedom, you had a choice. Why did you take this course? Because you wanted credit. Come on, don't blame me for that. If you accuse me by saying that you are doing this topic because you want to get your salary, then you are doing this course because you want credit. That is all. But clearly these are all answers which are there. They're not going to convince the girl why she should be in this class. My last answer was this. I told her, don't ask me why I'm doing this topic. I don't think I can give a good answer for that. I told her, I can help you think through a topic. I'm going to give some ideas. We're going to take a small topic. I'm going to give a few definitions. We're going to explore this topic. I am going to provide you thinking skills. Given this, can you do this? I'm going to provide you thinking skills. And I told her, I believe these thinking skills are transferable even if you branch off to any other subject later on. I told her, the facts of trigonometry are not transferable. The facts of physics are not transferable. The facts of biology are not transferable, but the thinking skills are transferable. I believe she was very convinced, but I think that this is the best answer we could give. And that should be the basis of any teaching program. If a teacher enters a class and does something, I think the idea must not be to finish the syllabus, though that's also there, but still the bottom line must be to provide thinking skills for the youngsters, for everybody for that matter. So what I am trying to do now is not to just give you, but probably revive, I should say revive the thinking skills which are hidden in most of us. So food for thought. So I had an American colleague of mine, we had a discussion on teaching, and she said, Ravi, it was a general discussion, and she asked us this question. She was a counselor, and we had a meeting, and she asked us, hey guys, would you like to sit in your own class? She asked us teachers, a group of teachers, and she asked us, would you like to sit in your own class? Oh, that was a tough question. Honestly, many times no. If you ask me, Ravishankar, would you like to sit in your own class? There are many times where I am not delivering what I should deliver. Not all my classes are interesting and engaging. So there are classes sometimes which I myself wouldn't sit in the class. Because to engage students for whatever time you have and make them think all the time calls for a lot of preparation on your part, which honestly even today I don't do that much. So that puts a big responsibility on me to providing thinking skills is not an easy job. It's a very tough job, a lot of preparation has to go in. But every time I enter a class, this question kind of haunts me. I remember this lady's name, Judy Thomas, a very interesting lady, very thoughtful. You can always, any interaction with her, you can have some takeaways. Very interesting person. Okay, now I'm going to go to some more serious stuff. So I've been pointing fingers on this pendulum experiment. You did that, you did this, you didn't do that. So you can ask me, okay sir, fine, you tell us what to do. Come on, let you tell us. So a discussion would be incomplete if I say, I just point fingers and close the topic. Now the topic begins. Now let's say you're going to investigate a pendulum. What is it the student is going to investigate? Now that is a tough question. Because the student has to now, let's say you give the pendulum to him, the student's task is to come up with a research question. What is he going to do? Now would you say, I'm going to study the simple pendulum. Now that sounds very philosophical. I mean, it's very vague. I mean, there are no measurables in the statement. You need numbers, because I need to see numbers on the paper. And you need to provide me numbers which, when I do the experiment, I can verify. If you simply say, I study the pendulum, well, that is not scientific enough. So, these are the elements of an investigation. And I want you to tell me as I move on, is it physics specific, or is it biology specific, or economics specific, or chemistry specific? Formulate a research problem. Is it about pendulum? Is it about something in biology? I mean, you do economics, you do literature, you need to have a research problem. And I would say that's the toughest statement. The toughest part of an investigation is to formulate your research question. Honestly, I mean, I've been a physics teacher for many, many years, and sometimes people ask me, Ravishankar, why don't you apply for research? Now, then I say that's a tough question because I don't have a research problem. I don't know. That's bad. I've been not prepared well. And I myself can't frame a single research statement. So this is something inadequate in the preparation. And then design. What will you do? How will you go about the experiment? Variables, controls, data collection, presentation, analysis. Then after you get the results, compare with others. We do that. We don't do that. But of course, we don't need to do that because we always copy the reading from the last year's record notebook, isn't it? So there's no need to. In a way, we are doing that. It's just because you're copying from somebody else's notebook, and that's basically comparing with others. And conclusion, the teacher has already given you that, isn't it? If the teacher says your aim is to find G. So the job of a teacher should be to provide students or the learner these skills. And you can't hope to give all these skills in a single shot. It doesn't work that way. It's difficult. So over a period of time in the laboratory experiment, you have to select exercises or investigations where the student get to know these skills in a variety of experiences. So you could select, let's say, a pendulum, for example, to talk about design aspect of an investigation. how do you go about? As Gopal said, what we are told is, you enter the lab, the teacher tells you the heading of the topic. You have to find acceleration due to gravity. Now tell me, how many of us would think that this arrangement can help you to find acceleration due to gravity? That is the most unnatural question to ask. So that's terrible. The teacher tells you because the teacher has learned it before. And just simply telling you the fact to you, which is irrelevant for the person in front of you, because you don't really care for that. It doesn't matter for you. I mean, I've read it, therefore I'm telling you. What's the point? It's basically the case of a teacher trying to hold the stage. Isn't it? So, how do you think that this has got anything to do with acceleration due to gravity? Why would you want to thrust it into the student's head? Rather, you should ask him, hey, this is the pendulum. But it's important to give some information. Maybe you can say, hey, my friend defined this as, there's a mass of this pendulum, length of the pendulum, and you can allow it to swing. It goes all the way and comes back. It takes some time to swing. This is called a time period. So you give these definitions. Then ask the student, hey, what would you like to investigate? What would you like to investigate? The student says, I want to study its oscillation. Vague. That is not a proper research question. I want to find out how long it will keep swinging. Okay. Again, it's not a very serious problem. It will stop at some time, fine. So a good question, a good research statement could be, the students would say, Mr. Ravi, I want to take a string of given length, attach a mass, attach some mass, let's say 100 grams, I'll allow it to swing, I'll find the time of oscillation, and then I'll change the mass, like 200 grams, for the same length, because there are a number of variables the student has to understand the problem. Mass is a variable, the length of string is a variable. Probably I may have to also tell him that maybe it all depends on how much you displace it. Now when it's here, now let's say it takes some time to swing like this. When it's here, would it take the same time or a lesser time? Now as a teacher, I wouldn't want to tell all this to the student. The student has to find out. If you tell him, hey, keep the amplitude a constant. No, that's a no-go, don't do that. I wouldn't want to do that. The student has to find out. Because otherwise he's plugging in more variables than he should be. So the student has to find out. Maybe in the course of the experiment, if you see him doing that, you go and tell him, hey, think about this. Are you introducing more variables without your knowledge? Let's say the student changes the mass, and in the course of the experiment, for one pendulum, he gives an amplitude of, let's say, 10 degrees. The next one 20 degrees. Now I wouldn't want to go to him and tell him, hey, see this, you're changing the amplitude. That's not okay. No, don't do that. You tell him. Just think, have you altered any factor there? I mean, I would tell you, give some time to the student will find out. My experience tells me they will find out. Just give the time. But you need to be patient. So these are the things you must focus on in an investigation. In fact, I was working in the American school, right? So we had a teacher guide on how to help the students through the investigation. So look at these are the instructions for the teacher. What did the guide tell you? Problem statement, instruction for the teacher. The student should not be told the focus research question. Gopal said, find the acceleration due to gravity. You don't tell that to the student. Should not be told the outcome of the investigation. Get me 9.8, otherwise I'll kick out of this class, or you put 0 in the practical. Don't tell the outcome. Told which independent variable to select. Hey, here's a tabular column. Throw in, I mean, that's showing disrespect, isn't it? The way we teach the students is showing disrespect. I mean, we are in a culture where, students have to show respect to the teacher. I think it's time for change. It's the teacher who has to show respect to the student. If you give the sheet to him and tell him, do this, now that's gross disrespect. You think that this guy is an idiot who can't do things on his own, and you tell him, hey, just follow instructions. Don't do that. So don't tell him what to do. He has to readily learn the skills otherwise. Look at it. That's a skill which is not subject specific. And finally told which variable to hold constant. Don't tell him, hey, don't change the length. Don't change the mass. You don't tell him. He has to find out. Now let me tell you, what teachers tell me is, So we don't have time for all that. Well, if you merely follow instruction, you're also equally wasting time. You are actually wasting time then, because the student has not picked up any skills in your class through the year. Next, other guidelines. Design. How do you design? Means, ideally the student should make his own simple pendulum, not like what we do in physics lab. The teacher says, hey, this is a pendulum, this is a tabular column, just do it and get back to me. No, the student has to make his own pendulum. Maybe he can get a thread, he can get a stone. And then somebody said point mass. Is it really a point mass? That we'll debate later. Let him start. So, should not be given a focus research question. Do not tell him the outcome. And don't tell the apparatus to select. Don't tell the experimental method. Don't tell him how to collect data. And don't tell him how much data to collect. Some of us would start wondering, then why is this guy being paid a salary? Isn't it? Most of us think that the teacher's job is to tell you all these things, and a good teacher is probably one who gives all these things on a neat sheet of paper, and also finally gives you 20 on 20, because in the lab experiment, and you wonder why, if this guy is not going to do this for us, why is he getting his salary? Well, if he gives all this, he's spoiling you for a lifetime. The last one is what I would like to talk about. How much data to collect? I remember when in the lab, people do experiments, and always people have been told, you have to take many readings. You have to take many readings. For some reason, you have to take many readings. People come and ask me, sir, is 5 readings enough? 10 readings enough? I ask them, why do you ask me? You are the experimenter, you decide. Is 3 reading enough or 10 reading? You ask, you decide. Why do you ask me? See, again, what is it? See what we reduce the student to. This student is become a slave. And you know what he's trying to do? He's trying to please the teacher. So lab experiments are simply, a lab experiment is a situation where the teacher, you need to learn how to please the teacher. That's it. So, I tell them, you decide. If you take 1 reading and come back, obviously, how can you make a general statement with 1 reading? Then 5 readings. And from 5 readings, can you make a general statement? 5 observations, 10 observations, 100 observations. In fact, that's an interesting question to think about, because when can you make a general statement? With 1 you can't, with 5 you can't. Because I'll say, if I do the 6th time, maybe you won't get the same answer. Maybe. So ideally, I must be doing infinite observations, isn't it? Because how many number of observations you do, I'll say maybe I do the next time, it may not be the same thing. Sorry? More than 30. So 30 or 40, maybe some people can debate. The idea is, you just take as much as possible, and then maybe, and make a general statement with a caution. Saying that, hey, I've done so many times, there's always an element of doubt in it. There's always an element of doubt in it, but I have done these many times. There's strong reason to believe at this point in time that this could be the general result. Maybe there could be an exception tomorrow. Now, scientists formulate statements with that caution. There's always that element of caution. But unfortunately, when we do science in class, it's always like, there is this statement, that's ultimate, no change. It doesn't work like that. And every time you've seen great ideas have been proved wrong by somebody at a later point in time. So I wouldn't want to teach a topic in a class with that stamp of, what should I say, at the statement being the ultimate statement. An element of doubt is always important. A bit of skepticism through the course would do a world of good for the student. So these are some of the guidelines I had, and then data collection. Maybe I'll skip this. Okay, so that's the way you should be doing a lab experiment. Having said so much, let me go to some lighter stuff. I've been talking about pendulum. Let me tell you something more about a pendulum. I said the human body is a pendulum, isn't it? Now, there's a lot of nice things to understand about the human body and its motion. I'm going to talk about the physics of walking. So when I walk, let's see what all happens. We don't walk like this. Do we walk like that? We don't walk like that. And we don't walk like this even. It's look clownish. We don't walk like that. But look at the way we walk. And this leg goes forward, this goes forward. And this goes forward, this goes forward. We do it unconsciously, but that happens. So, this in technical term we call it in phase and out of phase. When your hands go like this, we say your hands are in phase. You go together. You go this way, your hands are not in phase, they don't go together. So when you walk, what happens is, again you can't walk like this. You can't walk fast and swing slowly. Just try this. I can't. If I walk fast, I have to swing fast. I don't know if you have tried out all these things. If you walk fast, you have to swing fast. And not only that, when you start walking really fast, look at it, you can't start running like this. You can't, you'll trip and fall. When you walk, you have to bend your hands as well. It will automatically bend. See this? And you've seen all runners. They pick up speed, they'll bend. So that is the reason why you bend. I'm going to talk to you about a little bit about that. So basically, your left leg, right hand in phase, right leg, left hand in phase. Frogs will be probably different. They'll hop and go like this. So because their legs are in phase, ours are. It's not like that. Also, when you walk, this is kind of a pivot, and your leg swings like this. It's like a pendulum. It's a complicated pendulum because this portion is a pendulum. There's another pendulum. The foot is another pendulum. The toes are pendulum. So multiple oscillators. So, and how do you walk? Look at this. You put your foot first. This part of the foot goes in front, and then you release your toe there, and then with this as the pivot. Pivot is a fixed point, something like this. Then you swing this foot forward, and then you bring a foot to rest. So let me repeat. This foot is fixed. See what happens. You throw this leg forward, and slowly there, you have a toe in contact. And then, this ankle, right? This ankle, it touches the floor, and then you release. Now this, in physics, we call, it's a pendulum. It's kind of a reverse pendulum. For example, this is a pendulum, right? It's a compound pendulum, because this is mass, and it swings like this. But imagine a pendulum like this. The pivot is here. It swings like this. The human body is something like that when you walk. Because see this. Imagine Ravi as a rod, like a ruler. See what I'm doing. I'm oscillating like this. So imagine Ravishankar as a rod. This is my foot. My body goes like this, approximately. So my motion can be described in terms of a special point in my body called the center of mass. So if you look at the center of mass, it will hop like this. It will go this way and keep hopping, because you have to go up and then fall. So walking is actually, you kind of get up, then you fall, and you prevent your fall. Let's say you don't put the other foot down. See what's going to happen. Suppose I do like this. I'm going to trip. So what you do is you kind of get up, right? Go up a little bit, then you start falling, but you have been trained to put the other foot forward, and then you arrest your fall. So basically it's a series of falls. An interesting question is, what is the difference between walking and running? See, you call this as walking, fast walking, but how fast can you walk? Is there a limit? How fast can you walk? Now, I've seen this race walking. Race walking, they don't walk like what we do. They do like this. You seen that? It's a nice trick. It's a nice trick to increase the speed. Normal walking, you can't do that. You can try that out. Ask somebody to walk normal pace, and you walk race walking, you'll win the race. There's a smart trick there. So you do, look at the hip. The hip will just swing this way, and it will swing like that. The idea, because in race, walking is, your feet should be on, one of them must be on the ground all the time. Look at running. When I run, when you see from distance, you probably can't see. There will be a time when I'm airborne. Let me try. See? You can see me, both my feet be off the ground for a fraction of time. In a walking race, you will be disqualified to do that. Because you can cheat, isn't it? Because you need to walk really fast. So you may start running. So how do people find out whether running or walking? So I'm going to do a little bit of math on the physics of walking. Because how fast can you really walk is the question. So a small piece of math. Can I have a pen? Yeah. Can I write here? Can I? It's a bit complicated. Don't bother. But I just wanted to appreciate the fact that when it comes to walking, there's so much in it. Because how many of us would consider what is the difference between walking and running, and what determines how fast can you really walk? So it's something like this. Let's imagine Ravishankar like this. When you walk, let's say you're walking the fastest now. That is, even if you increase speed a little bit, you'll jump off. That is, both your feet will be off the ground when it is just off the ground when you're walking fastest. So those of you who are in physics will realize that you're just off the ground, there's no normal force. So I'll kind of remove the floor here. So this is your center of mass, let's say, and for Ravishankar, see my height, my center of mass will be somewhere here. Let's say here, it's just an approximate number, don't bother. This is about 1 meter, maybe a little bit below and above. On an average, let's say 1 meter. For a person like me, about 1 meter, it could be 1.3 or 1.2, it can be 2 meters. About 1 meter, it's okay. So when I just take off, I would go like this, right? When I'm at just this is the maximum speed for walking, which I'm almost airborne, which means there's no normal force. So I'm going to go in a curve like this before I land on the ground. So I'm going in an arc of a circle like this. Now that circle will have a center and a radius of curvature. It's not a good diagram here. It's almost, it's not a good diagram. Can I have an eraser? I had. It's not a good diagram because it's almost my height. The radius will be almost my height because my foot is the pivot. So it's kind of this height. R will be roughly the height of the center of mass. And when you go in a curve like this, you need a centripetal force. And you can say mv max squared, that's the formula of a centripetal force, is equal to m times g, because that's the only force acting on you. So basically in technical terms, those of the physics people can kind of understand this to be the centripetal force is being provided the weight force. The mass gets cancelled off and your V max is square root Rg. So let's see how much it will be for Ravishankar. What's the maximum speed Ravishankar can hope to walk? So it will be about, G is 10, will bill your teacher Gopal. Right? About 3 meters per second. That's on the higher side. I've read that it's about 2 meters per second, it's roughly 2 because there's an approximation here. It's about 2 meters per second. But race walking you can do faster because race walking is slightly different. So it's about 2-3 meters per second, 2 meters per second, 2 meters, we can try it. No, it's about, yeah. In 1 second you can cover about 2 to 3 meters per second. So that would be the maximum speed you can walk. You can't walk faster than that. The interesting thing about this is, look at that R. What is that R? R is the height of my center of mass. A taller person has a slightly greater R, so he can walk faster. That explains why kids can't walk that fast as adults do. Because their height, we'll call this height, it's much smaller, so they can't hope to run that fast, they'll start running. They can't walk that far, they can start running. A taller person can clearly walk faster. Another interesting thing to think about is the role of G. Now you walk at some speed on earth, right? What if you take it to the moon? If I go to the moon and you start, let's say you want to walk really fast. Well, let's say you can really do it. Because on the moon the G is much slower. So your maximum walking speed will be so much reduced. So you can't walk that fast. So have you seen some of the videos where they do the moon walking? because they can't walk that fast, what they do is just hop off. They just hop. So that's the real moon walking we should be talking about, right? Moon walking means we think of some of this Michael Jackson or somebody, I don't know, but that would be moon. That's why they start hopping, because they can't walk that fast on the moon. They start hopping. So that's the math behind this. So that is the clicker. Yeah. What happened to that? Oh yeah. What happened? Yeah, just you can see that kind of hop that way, and that's an inverted pendulum which I was talking about. Yeah. So there's so much to a simple pendulum. Sometimes, each time I teach simple pendulum, I wonder, is it the right term for it? Should you be really calling the simple pendulum as a simple pendulum? It's probably one of the most complex systems you come across. And you will agree, after listening to what Manigandan had to say, and the complicated equation he threw at us. So certainly the pendulum doesn't seem to be that simple. I've been a bit critical about the near stale laboratory practices we still follow. It's time to make the classroom more vibrant and laboratories more active. So the chemistry laboratory, sometimes I wonder, it's only the chemicals that react, not the students, right? And the students' spirit seemed damped, fun there. When they enter the physics lab, and the pendulum probably provides an opportunity to make them bubble with energy and curiosity. And this presentation is a call to inject life back into the physics laboratory. So my presentation you can treat as an invitation to my teaching colleagues to use the pendulum as one of the most amazing teaching tools, and probably provide a whole range of skills to pick up and transfer into whatever stream they branch off later on. So a proverb of the times we are in, the taste of the pudding lies in its making. I happened to see this proverb the other day. What's that actually? It's like, what is it? What's the actual proverb? The proof of the pudding lies in its eating or something. Then I modified it. It's my quote, by the way, copyright. And then, so what's a good classroom? The Powells are two educators in the United States of America, and I had an interaction with them years ago. And I asked them, Mr. Powell, what would you call a good classroom to be? And they said, a good classroom is one where there is intellectual discomfort and psychological safety. Intellectual discomfort, because you need to stir the student and put them on the, you can't, what happens is we think we are doing a good job by creating a lot of comfort for the students, telling them what to do, giving them the laboratory sheets, telling them the result. No, you're spoiling for a life. But real investigation is actually difficult. And don't you think real life problems are like that? Real life problems, you have to come up with new solutions. Otherwise, it's not a problem at all. If it's already solved, how come it's a problem? So, I think the critical part of learning is the discomfort. You need to train students to enjoy the discomfort, because only then you learn. So I would not miss an opportunity in a class to provide that bit of discomfort to the student. At the same time, one has to be cautious in providing psychological safety, because you can't put them down. So you tell them, hey, it's okay not to know. If you make a mistake, it's fine. Come back. Let's talk about it. So give them the opportunities to rectify on the own, rather than you telling, hey, this is wrong, do it again. So it's a very interesting statement, which I keep thinking of. Whenever I enter a class, this keeps ringing in my ears. This is my friend Louis Rosenblatt. He's an educator in the United States again, and I had a very interesting conversation. And he's written a book. It's called Rethinking the Way We Teach Science. And he says, we would do well to remember as we teach what he had been like a student. Let us invite the students to learn and set aside our bullying. My friend was saying the teacher was sitting in the knuckles. It's classic case of bullying, isn't it? The teacher's bullying. I would say the teacher is bullying. So I think we teachers, including me, tend to forget that we were there once. And I think we tend to teach the way we were taught. So that explains why things have not changed much. In fact, I had read another article, I think this was by Al Gore, you know Al Gore, Al Gore's the speech writer. He's written a book. The article is called School is Out. He says school is gone, outdated. He says, now you go to a bank. Banks, see how they look. They've changed. You go to a corporate office. How they look. They've changed. I mean, you go to any business establishment and compare it 50 years ago, 30 years ago. They have changed. You go to a school. He says they're not changed. He says they're not changed. I mean, whether they should change or not, this is a different story. It's not like you have big buildings and you've got air conditioners. Learning is going to be any better. I mean, certainly you don't need an air conditioner room to teach Pendulum. I don't think so. I don't think the schools really need to change. If changes to mean that you need air conditioner rooms and nice cushion chairs for the students, provide them refreshments, if that is what the change you're thinking about, now that's a no. The change is about the processes. So it's a very interesting statement. And another nice quote from Carl Sagan, one of my favorite authors. It's a great book to read, Dim and Haunted World. He says, bright, curious children are a national world resource. They need to be cared for, cherished and encouraged. But mere encouragement is not enough. We must also give them the tools to think with. And that's what elders can do and parents can do. Many parents come and tell me, Ravi, I am not a physics student. What do I do with my kid? How do I teach him physics? Well, even my mom was not a physics student. My mom is economics, my dad is textiles. Nobody in family is physics. I'm probably the most abnormal person in the family. Something must be wrong with me. So you don't need to do that. You don't need to know the subject. As a parent, I mean, many of you will be future parents. So you could encourage and tell them, hey, think like this. Hey, think about it. If you know, you tell them. If you don't know, ask them to refer a book. Then it's okay. What you need to do is to let the kids understand that it's okay not to know. It's okay. I mean, if you don't know something, it's fine. But explore. But try to find things on your own. I like the last line, give them the tools to think with. And that's my reference. So, thank you. Keep thinking. We have a question and answer session also? Yes. Yeah? You must ask questions I must know the answers. Otherwise, don't ask. Your teacher was like that, Gopal? Oh, you can't even ask questions. No way.
Yeah, exactly. You can't ask questions.
I remember when I was a student, I asked a teacher a question in the class. The teacher said, don't think you're Einstein. Don't think you're Newton. Are you questioning Newton? That's the reaction. I mean, I had a simple question. The teacher could have said, I don't know, or I'll let her and find out, whatever. But she really fumed at me saying, are you Newton? Well, I didn't react, but I always wonder how I should react. Well, number one, the teacher is not Newton. I can certainly question the teacher. The teacher says, hey, how can I question Newton? Fine, given, I won't question Newton. But you are not Newton, you are not Einstein, I can certainly question you. Number two, I am not questioning the teacher, I am questioning an idea. We are not targeting individuals, we are targeting an idea. Lastly, who said Newton cannot be questioned? I have the right to question Newton himself, as well Einstein did it. The teacher has lost his case already by quoting Einstein and Newton, because what did Einstein do? Einstein corrected Newton. So nobody said Newton cannot be corrected. So it's not that you got to be right all the time. It's okay. Yeah.
Okay, Newton had a very abnormal childhood, by the way, before he got to where he did. Simple question. Please. How do you finish your syllabus?
Ask my students. Do you finish the syllabus? A better question to ask.
Yeah. I assume you finish your syllabus.
I am in the process of admitting students by next year's batch. I think your question will put me in trouble. So I'll answer your question private. Anyway, I think I do find time to finish the syllabus. I mean, it needs to be done. To give an honest answer, I think I always finish the syllabus. But I'm not the ramrod approach teacher. I do 100 prompts in an hour. I don't do that. Maybe you can say that's a bad approach.
99?
99% syllabus?
No, 99 problems?
No. I do like 10 problems sometimes. Sometimes I do one problem for 1.5 hours. You can find fault with that approach. But I believe that's the approach. When I try to do a balancing act, I'm not claiming that it's the best approach. But again, which is the best approach, you tell me? I mean, that's a question for debate.
No, Ravi, I love the way you approach it.
Yeah.
I mean, some of my teachers were like this. I'm a master's in physics, same, just except that I'm no longer in physics. I was a master's in nuclear physics. Now it's unclear physics for me. Yes.
Same here.
But I wouldn't have gotten there if I didn't have good teachers. Now, with the education system we have today, where the focus is on finishing the syllabus and then scoring marks, this kind of investigative approach, I mean, it's fantastic. But how does it gel together?
It's difficult. It's difficult. I don't have an answer for that question, but I think you need to do a balancing act there. Because if you go for a ramrod approach, I mean, if I do that, I think I will say I have my approach to teaching is this. I have two options. Either you do the ramrod approach. Second option, don't teach. Right? I have only the second option. I mean, if I have to teach just for the exam, I think I'm not preparing the student for the long term. I think I'm doing disservice to the student. So I think it's not preparing them for the long term. So I think exam would be an excuse rather than a reason. I wouldn't accept that as a reason. I think I've been able to fairly complete portions, and I mean, I wouldn't say I'm the best in the field. I'm not going to make any such claims. There are better people, fine. But I think this is the way I can work. And I always have an option of, do I teach the subject or do I teach the student? I want to do both.
You guys heard of Dolly? Dolly the sheep? What happened to her? The first clone sheep. We need to clone him. Get more of him, right?
But did Dolly live that long?
You said we always have to experiment. The same thing doesn't have to happen.
Well, hopefully better. There's a chance.
Thank you, thank you.
I appreciate the question, but when I don't have an answer. I don't know whether I really can do a balancing, but I try to do it. But if I go for a ramrod approach, I believe I may lose interest. I don't want that to happen.
How do you think, I mean, this is brilliant, okay, and how do you think this will apply for first generation learners? You know, particularly if you're taking it for rural schools and for first generation learning schools, we have a lot of difficulty in actually telling the teachers to be moving from a fixed mindset to open mindset, keeping with open questions and so on, because they come back with a lot of challenges saying that the kind of environment they're coming up with and for the kind of syllabus and the volume of syllabus that we have, and giving them the sufficient time and actually allowing them to ask a lot of questions and coming back. They seem to have loads of problems saying that there is a time constraint, and of course we don't have the liberty to go back and reduce the syllabus even though we would want to do that. Particularly for the first generation learners, I'm sure that some of the systems are changing in the so-called getting little lenient with some syllabus and some boards are doing it. But still it's really getting difficult to get them on par, and even though we really want them to be on par with the rest.
I wish I had an answer. See, I think that's where education was the greatest problems of our times. And one of the wonderful problems to handle. Now, I think we rather face it or pretend, rather than pretend that there's no problem, everything is fine. Now, those of us who tend to finish portions, train for exam, I think we are not facing the problem at all. We are just pretending there is no problem. I wouldn't say it's a problem. For me, I would want to look at things as issues. Let's not look at things as problems. Let's look at them as issues. Here's an issue. I mean, you have to find a way. Come on. Instead of saying, well, I can't do much about it, I'll do the same thing. Well, it's a difficult question. And that's a challenge for educators. And I think it's important to think about this issue. I mean, I don't think it's about finding the solution for it, but I think to start thinking about it, it's much like solving any problem for that matter. You know, how you start solving any simple problem, you struggle through it for some time, you don't get the answer, you make the mistake, come back and rectify, you do all, that happens at every level. So I don't have a solution for that, but I think it's important to accept, hey, this is an issue. And if there's an agreement on, if people accept, hey, and it's not about blaming things, you know, it's not like blaming X, Y, Z, W. It's not about that. We are a part of system. I mean, I don't like talking about you being out of the system and then pointing fingers. You are a part of the system. So I think it's about thinking about it and trying to find some solutions. It may not be the best solution. I remember when I joined American school, my principal called me and said, Ravi, I know you from an Indian system. And he continued, I am not claiming the American system is the best system, but that's what we follow here. I think that's a very honest response. Here's a principal who is very honest, right? And he doesn't claim that's the best system, but certainly he's somebody who's thinking of doing things better, and he wants a new teacher to do better. So I think that's this principal is being very honest. He's not claiming it's the best system. I think we claim to do that in here. We think everything is fine. Well, it's not. It's not. If things are fine here, then why don't many students from abroad come and study here? It is our students who go and study abroad, not the other way around. Not in the proportion, at least in science. I mean, I don't see that happening. Not in science, certainly. You don't have American students coming and studying here in big numbers as Indian students going there and studying there. There's something happening there, and one has to address that issue. Well, again, I don't have good answers.
But I think I can support what Ravi is talking about. There is this TED talk by Professor Sugata Mitra. It's called A School in the Clouds, and Rajshri, I guess you've seen it too. So it's proof that first generation learners can actually be very good. If you haven't seen it, it's on the TED site. Go look for School in the Cloud by Professor Sugata Mitra, where his experiment was, it's called a hole in the wall experiment. He puts a computer in a hole in the wall, and children from the slums come in there and learn about it with absolutely no help. Absolutely no help. So his theory was that schools were set up by no one from the UK, right? By the British bureaucracy, because the empire had gone so far away, so across the world, they needed people to manage it, and they needed people to think exactly the same way. And that is why schools were set up, so that they could churn out person after person who thought the same way. So his experiment was, if I change that, would it work? And whatever Ravi talked about, I think that's what happened. People did, learn on their own.
To add to that, I believe people learn on their own if you provide the freedom. I think freedom is the basis. You give the freedom, people, we are in the culture where we think that we have to teach them learn. I remember I had a conversation with an Indian teacher, an Indian colleague of mine, and she said, how can you talk like this? I told her, you don't need a teacher for learning. She said, how can you even talk like that? Teacher is like God. I said, okay, fine, accepted. And then I asked her, from where did I learn Newton's laws? I told her, from my teacher. My teacher learned Newton's law from where? Who? From his teacher. Goes on and on. Now, this question keeps going. Where will you stop finally? You will have to stop with Newton. And what would the teacher say? From whom did Newton learn Newton's laws? Did he go to a class where the teacher told him, hey, Newton, take a notebook. I'm going to teach you Newton's laws and you're going to learn it from me. The teacher was shocked. She was not prepared for this sort of argument. But just to tell that you really don't need a teacher.
What would be an effective class for one of your students? Can I hear from any one of your students as to what was your most effective class, and how much do you value feedbacks?
You are asking about my class in specific or any general class?
Anyone from your class, it's not necessary that they should answer, you can answer for them.
No, I don't mind, they can ask. You can do two things. How should a general class be, and if you want a response specific to my class, I'm okay. You could be critical as well, I have no issues on that, that's okay. You could be critical, that's okay. You don't need to give a nice feedback, it's okay. Feedback could be other way, it's okay.
I would also like to know how much do you value feedback? I'll recollect my first class, it was in 11th grade, it was...
Ashwin, could you just get up for the other Don't mind.
Ravi walked in, we were all talking. First of all, we didn't know Ravi was a teacher, we thought he was a student. Really young.
Somebody thought I was an electrician years ago. I remember that was first day in Padma Sheshadri. I entered the class, and I I was not in the formal attire or something. I don't like all that. So I entered the class, and this guy, some of them thought, why? And I told all of you, sit down. And these boys told me 2 years later, and they told me, sir, when you walked into the class, we were wondering why is this attender or electrician coming to the class and telling us to sit down. So, anyway.
Yeah. Usually what we expected teachers to do is like, shh, silence. Ravi walks and says, we all realize after some moments that he's a teacher. He's like, continue talking. He walks up. This class primarily starts with first rule of Ravishankar is this. You do not say a word without defining it. If you want to use a new word in Ravi's class, you have to define it and then use it. And I still remember it started with not nuclear physics, not quantum mechanics. It started with velocity. There we started fumbling. And from there it started till 12:10, we were still fumbling. Whenever we had to use a new word in physics, we had to define that ourselves, and then only we can proceed to make a point. That's how our class experiences were. And when it comes to feedback, he does not give a questionnaire and asks you to grade on 1 to 5. No, he gives a plain piece of paper, says, write. That's pretty much his feedback. And I can say with 100% guarantee, he reads every one of those feedbacks. And mind it, his classes are not 45, his classes have 400 people. And that goes on for 2 batches. So he reads every one of them, make sure the best ones are read out for the next class. So yes, his classes were beautiful. I keep him on the levels of Feynman in terms of teaching. And yeah, he takes his feedback extremely seriously.
Just 1 minute. 1 minute. So.
Define best one. Best one positive, best one negative, best one neutral.
I think the best ones were on ray optics and interference.
No. What type of feedback? When you say best.
Oh, that I can't say it out. No, I exactly don't remember those feedbacks per se. But yeah, it could vary from anywhere between I didn't like these classes, I didn't like these topics, they were particularly boring, or I found these extremely well. I think most of them were very good feedbacks.
Can I interrupt? Yeah, please. Ashwin, by the way, I'm not very regular in taking the feedback these days. So let me be a bit honest in it. I mean, for some reason, of course, people tell me directly. That's there. So it's nowadays I don't give a sheet to them and ask, because it's too many sheets, and then I go through, and it's a bit difficult. But of course, people email me and ask and whatever. So that sort of a feedback is still there, because it's not necessarily on a sheet of paper. People write to me or text me or something like that. So I do take feedback, but not in the very formal sense as not these days, but I do take feedback in a very informal sense. And feedback, I remember the first time I took feedback was maybe in 2002, and I had an extremely good bunch of students on Padma Sheshadri. One of the amazing bunch of kids I taught in many years ago. I thought I did the class very, very well, and I ventured into the idea of feedback. I thought everybody is going to sing in praise of me. You know what happened? Brickbats. I got blasted left, right, and right, center. I just got blasted. People didn't like, many of them didn't like the class because they said I went too deep and they couldn't follow the class sometimes. But there are a few others who could follow really well. Out of a class 40, 10 could follow, 30 couldn't. That's bad. Only then I understood that I need to reach everybody. So it was a very difficult thing to swallow them, honestly. I was not prepared for it. I didn't think that I'll get a negative feedback, but I did get a negative feedback. That was quite upsetting, honestly, because I didn't expect, I was not prepared, I would say. It's not upsetting in the sense I didn't expect, I didn't know how to react. And some students said that, that one student said, you spend too much time on a single topic. I replied by, I said, I'll continue to do so. Yeah.
No, it's not a question, it's just continuing. I like the demonstrations. Like usually we are used to physics theory being a separate stream and practicals being like separate. So he was combining, like he will finish one topic, bring something live for us to see. And I would hesitate to ask questions and he would really encourage me to ask. And I remember one session on interference, I was asking continuously and not letting him teach. It was like bombarding with questions, why the slit has to be so small, why is there a slit before the 2 slits and all that. So he's very patient with all his questions, or he'll say, answer it after class. So I enjoyed both the practical side of physics and encouraging me to ask and then answering all of them.
I believe they have a voice. Let them use it. We have a voice. Talk.
Yeah, I would like to add to the point. Usually, at the beginning of 11th grade, he usually hands out a book. In the first page, he writes a letter. At the end of the letter, he attaches a sentence which says, "There is no such question as a dumb question." So I like that sentence very much, and till date, except him, I've never met any teacher who says this. So, thank you, sir.
Good to say this. There is no question as dumb question. Ravi, do you remember who says this to us? By the way, both of us, learned this from a professor called Professor Ananthan. So he used to tell both of us, there is no question as dumb question. I'm sure he has percolated it to almost few thousand students. Amazing. So what Professor Ananthan has done to us, he has done it to few thousand students. I'm very happy. Thank you, Ravi.
Well, it wouldn't be complete if I don't mention a word about Professor Ananthan, whom he has been referring to. It is Professor Ananthan from whom I learned all my physics. And he used to tell us that if you want to learn something, you need to accept your ignorance. You need to be honest about that. And that is what I call as intellectual honesty. If you pretend you know something when you don't, that is gross intellectual dishonesty. And you're not going to learn that way. It's not going to happen. So he used to tell that if you don't know something, just accept it. It's okay. And have the urge to learn. You must have the continuous urge to learn. I think I still have it. And I still find physics very engaging and exciting. And I think that's what we learned from Professor Ananthan. We learned how to learn. To put it simply, we learned from him how to learn. And that's the big thing we learned from him. It's not about physics. I mean, of course, we talk only physics, but I think many of us, given, let's say, do biology, I think we could do well. I remember I taught biology once in American school for 7th standard. The principal called me and said, "Ravi, I want you to teach biology for grade 7. I said, Mr. Crouch, I don't know how to teach. I mean, I knew biology, but I didn't want to take the trouble of teaching biology. You know what he said? "Ravi, it's easy. All you need to know is just a little bit more than a 12-year-old kid." I loved that idea. I said, "Yes, I'll teach it." And I taught biology that one particular. So I have taught physics, chemistry, math, biology also I taught 1 year. And that was my most exciting class that particular year. 7th standard students. It was lovely. The best class of the year was my biology section, grade 7.
I think we have time for 2 more questions if you want to ask.
Yeah.
Yeah, nowadays getting a good teacher or a better teacher is being question marked. The grade of the quality of teachers is also degrading, quality of students is also degrading. What we should do for this?
Sure, you want to say that in front of all the students?
No, it's not. As when you are a student, the level of the student level or whatever the grade.
Maybe Ravi, I'll take that question. Yeah. So what should we do about teachers' quality being degraded, right? First of all, pay heavy salary for teachers. First, okay, don't go for anybody who is coming out of IIT or any big institute. Become a teacher first, and let them be paid more than the software engineer. Okay, once they are paid more than the software engineer, then those who are interested in teaching, like Ravi, okay, will. Even myself, if I had been paid more, I wouldn't have joined Infosys. I worked for Infosys for the past 16 years or so. We both were learning physics. So if I were paid at that same day, same salary, what Infosys paid me, I would have become a teacher. So pay the teachers more salary. Those who are interested, give them more salary. Those who are interested in teaching. And most importantly, like Ravi said, change the system. Everybody, parents wants their kid to get into IIT first, if not next is Anna University and then so on, okay, where there is a placement. People are getting into IIT not because IIT is a great place to read or Anna University is a great place to read. By the way, I am from Anna University, so it's not that people they are going there because It is the placement is excellent, right? So please don't go for placement. Don't learn for placement. Learn for knowledge. If your parents are willing to do that, because kids will not know. What will they know during that time? So don't go. So it's all about money finally. What happens? We don't want education. We want money. If I get good marks, I will get good placement. If I get good placement, I'll get good company. If I get good company, I'll get good salary. So finally, knowledge is lost. So please, I'm extremely happy and proud and many times jealous about Ravi for being able to continue in this field with such a great honesty. And I'm extremely surprised and thrilled by so many people attending, and it can happen only with a teacher.
Well, it just means I'm not good to do anything else. It just means that, right? I'm reminded Bertrand Russell quote. Bertrand Russell said, "Those who can do, and those who can't teach." He said, "Those who can do, and those who can't teach." So, yeah.
The last question.
Hey, it's been a while. How are you? So my question to you is this. It's been a while since I've attended your classes and your lectures. And your main focus, while it dials down to, is how to make the process of learning effective. How to learn the process should be more effective. So have you made it better? Have you found ways to make it better? How did you make the process better?
Wonderful. That's an absolutely fantastic question. That's a question which bothers me every year. And when I look back each year, right, this year, by the way, I think I didn't do a good job last year, to be honest. I mean, not only you're an old student. I have students from this year's batch, previous batch, last few years I've seen people. Soumya said something. I teach interference in a much better way than what I did for you that day. Seriously. So I make a conscious attempt to do better. So it's not the best, but I'm trying to make it better. I do think about that. But that's a very interesting and important question, because that's where you're focusing on the process. I try to do it better. I wouldn't say it's the best, but certainly when I look back, there are a lot of gaps.
I think probably I'll ask the last question of the day.
Last question, yeah.
Running short of time. So, Ravi, you talked about simple pendulum and the physics of walking.
Are you sure I won't beat you in the knuckles? I have a scale.
Yeah, I'll maintain my distance.
Careful.
Right. So, I have this question to you as a teacher. See, as a student, I'm sitting in the physics class, and you're teaching me physics of simple pendulum, and you're also relating to the walking also. Now, biology teacher comes and teaches about walking, but she draws a strict boundary of its biology and only human parts and so on. Maths teacher comes and says, this is a formula, the maths teacher also talks about walking. Now, it is left the student to me actually to integrate all these things into one and comprehend what is walking and what determines walking actually. So why is the pressure on student to integrate all these things? Why are teachers putting boundaries on subjects and not giving integrative thoughts?
Well, again, see, that's why education is a great topic for discussion and debate. It's honestly, it's a big topic in the United States. I mean, I can tell you all about the United States because I meet a lot of people from there. Education, I am very interested in physics education, and I know many educators there who are involved in it, and they do a great job thinking about all these things and education in general. But here, still, it's not a big field, and maybe I've not met people who are into it, but it's not considered a big topic for research. That's why it's a great topic for research, and you have got people to come into that field, because you need to see it's a big crowd in front of you. Don't you think you have to make the best use of the time? So it's a difficult question to answer, but somebody has to ask this question. The problem probably is because nobody has asked this question. So once you start asking questions, you will find ways. I mean, my friend asked me whether you can finish syllabus. So that's a question I have. You need to find a way of doing it. I mean, you need to finish syllabus, you need to teach the subject, you need to do that. I mean, it's a challenge, but I think it's one to understand there's a challenge in front of you and think of some solutions. You need to find out. Well, it's a big question. I don't know that I don't think I have an answer for that, but it's an important question. In fact, the last book I mentioned was, I read some of this stuff from this book, Physics of the Human Body. It's an amazing book, and it's a biomedical engineering department, some United States university. Until I read that book, I thought I knew physics, and I did not. I knew that I did not know biology. It's okay, and I thought I knew physics. After reading that book, I understood I don't know both. So it was an amazing book. That book is it's talking good physics as well. It's a biology guy talking serious physics and serious math, and you see all calculations in the book. All calculations, the math part is there, the biology part is there, the physics part is there. It's just amazing, and the chemistry, by the way, the energetics part, the energy change in the human body. It's a lovely book, Physics of the Human Body by some Irving, I forgot. I don't remember.
Thanks, Ravi. Thanks a lot. I think.
Thank you for the patient listening.
Deserves a big. Thank you so much for inspiring a lot of us. We'll definitely go back and try to transfer the thinking skills from across one domain to another domain. At least in workplace, because in workplace sometimes we feel that we have to strictly follow the code. Customer support call, good morning sir, welcome sir. Follow the code and then simply follow instructions. Like slaves and this thing. At least I think some things will go back and change. So
is that in every job, by the way? Even teaching, in a way, I'm also a slave. I have to finish the syllabus. I'm also a slave. It's there. But you need to find ways of making your job interesting.
I'll request Rachi to kindly come and give a memento of it.
Thank you. So please call me often, so they'll get a gift every time.
We'll literally hold on to the statement.
Thank you.
I want to thank Ravi and thank all the audience here who come a long way to listen to Ravi sir, and also people who are watching on the live streaming. So thanks a lot for coming for K community. Please do keep come and then come as speakers also here and share experiences as learners or as students and so on. So please you can contact me or we are on the Facebook and also on Chennai stream. As I told you, the video archive will be there on the Chennai stream. You can watch it again and again. So thanks a lot.
When is it posted? When is the video?
In 3 days it will come in the
3 days.
Chennai stream. So I'll put on the Facebook your page so that people can. Thanks a lot.
Thank you.
Thank you.